Good afternoon. Thanks for tuning in today to listen to this talk. I'm Mohamed, a research fellow at University of Surrey, working with Nishan's history, and this is a collaborative work with Arvin and Diego from Telefonica Research. I would like to start this presentation by a bit of background to set the context. Internet from space is not new. We already knew that few decades back when we started sending geostationary satellites to the space. With a handful of geostationary satellites, we can cover the entire Earth and provide internet access anywhere. However, these geostationary satellites have fundamental drawbacks. First, they are at 36,000 kilometers above the Earth's surface, which makes the round-trip latency between these satellites and any ground station to be around half second. Obviously, this is a very high delay and way beyond many of today's application requirements like video conferencing or gaming. Not only that, but also because these satellites are so far away from Earth, new technologies like beamforming might be difficult or even expensive to be implemented over these satellites. 4 or 5 years back, we started to see plans that will significantly change the internet infrastructure in space. Several competitors are working on sending thousands of small satellites to the low Earth orbit and forming what they call mega constellation to blanket the entire world with low latency internet services. Motivated by the cost reduction in satellite component manufacturing and the lower launching cost, the race to send tens of thousands of LEO satellites has started already. These satellites will not only provide low latency and high-speed broadband anywhere on Earth, but they will also enable a new class of applications that are currently not viable by existing infrastructure. And I'm talking here specifically about things like algorithmic trading between two faraway cities like Tokyo and New York. So motivated by this significant change of the internet we know today, we tried to take the first look at the performance of the only existing commercial LEO network, which is Starlink. With more than 3,000 satellites have been deployed already, serving more than 500,000 users, we tried in this measurement study to answer the following research questions. First, how does Starlink connectivity compare to other ISPs in a same location? Second, does the connection quality change over location? And the third thing is that, does the weather affect the performance? And for any measurement study, the key part is the data set. So how we collected the data? We actually have two data sets here. First, a data set collected from the browser extension. So we developed a browser extension and conducted an advertisement campaign asking users from different ISPs, including Starlink, cellular, and traditional fiber broadband to install our plugin. In this plugin, we introduced a new concept of page transit time, or PTT, which is the network-related aspects of loading a web page. I'm talking here about things like HTTP request, HTTP reply, and DNS. So basically, page transit time is the page load time minus other delays that are directly related to the browser and the device capabilities. So we wanted to eliminate any other aspects that are not related to the network. So we measured the page transit time for each web page that the user visits, as well as the page transit time for randomly picked websites from the Tranco list. So the second data set is collected by active measurements for throughput, latency, and packet loss. So we did that by attaching Raspberry Pis to Starlink terminals distributed over 3 continents, or three countries, US, UK, and Spain. And here's the simplified architecture of that. So we asked our volunteers to connect our Raspberry Pi to their Starlink routers through Ethernet cables. And all the measurement that we done over the Raspberry Pi goes to the Starlink router, and then from Starlink router to the Starlink dish, and then goes to the visible satellite and back again to the Earth through Starlink gateways. And this is the bent pipe architecture. At the time of this study, we had 3 volunteers hosting our Raspberry Pis, but now that number grows to 8 volunteers over 5 countries. For the browser extension, we have 18 Starlink users are using our browser plugin and 10 non-Starlink users. So this total 28 users using our plugin are distributed over 20 cities and 3 continents. So overall, we have more than 50,000 measurement sample only from the browser extension. I would like to pause here for a few seconds to do a quick advertisement on our ongoing work to build a global measurement testbed. So we are collaborating with different institutes and industry to build a global measurement platform for LEO networks like Starlink, something similar to Planet Lab or MLab. So please, if you are interested in cooperating on that, or if you would like to get access to some of the Starlink terminals, please get in touch with any of us, and we will be happy to discuss things further. Okay, so let's now go back to the results and trying to answer the first research question. Here we're comparing Starlink with cellular network, mainly 4G, and fiber broadband in the same location. So this is done in a single location near London, and the trace route goes all the way to a VM hosted in a Google Cloud platform in North Carolina. So what we can see here on x-axis is the hop count, and on the y-axis is the RTT in milliseconds. And this is the two curves for the fiber broadband connectivity and the cellular network using 4G connectivity. And then we have Starlink latency curve is something in between these two. So three things we can observe here. First, Starlink is still not better than a traditional fiber broadband. Second, Starlink has a significant delay in the second hop, and this is due to the bent pipe architecture that Starlink implements now. And the third thing is that all the three connections are experiencing the same latency on the last hop, which is mainly due to the traffic passing through or across the Atlantic from the exit point in London to the entry point in the United States. So inter-satellite links are essential if Starlink wants to overperform fiber broadband, for example. And we estimate that when inter-satellite links are fully implemented, we will see that latency curve for Starlink might be something similar to this curve. So we no longer will have this high spike here due to the bent pipe architecture. We'll have a lower spike here because now we're working on inter-satellite links. And also the latency at the last hop, it will not be very high like this due to the crossing the ocean. Rather, the Starlink will rely on their satellites to move between different continents. So the traffic will be passing through different satellites rather using the optical fiber connectivity across ocean. So that will slightly reduce the latency here on the last hop, but it might increase the number of hops. Okay, so this is the performance in a single location, but different ISPs. Let's now look at the only Starlink in a different locations. And this result came from the active measurement again on Starlink terminals. And here we have 3 CDFs for the downlink throughput of Starlink across London, Barcelona, and North Carolina. And what we can see here is a significant and a clear difference between these 3 cities. For example, the median throughput in North Carolina is around 40 megabits per second, while it's something around 160 megabits per second in Barcelona. One justification of that is because the difference in the number of served users per city. So at time of this study, Barcelona had recently got the Starlink service, which means the number of served users in Barcelona at that time was much lower than the number of served users in the United States. In the paper, we took a deeper look to prove that the Starlink is more congested in the United States compared to Barcelona, for example. So please refer back to the paper for more details. But also, this has been confirmed by a recent reports from Ookla speed test that confirmed that Starlink got slower due to the limited available capacity in some countries that Starlink currently operate in. Okay, now we know the throughput performance across different cities. Let's now focus on the throughput performance in a single city, but we vary or we change the congestion control. Again, this is from the active measurement dataset, and we compare Starlink downlink throughput performance with different congestion control. And we benchmark that against fiber broadband on fiber broadband connectivity. So 3 things to observe here. 1, BBR achieved the best performance for Starlink. Second, how the achieved performance using BBR is only represent 50% of the actual capacity that Starlink link can achieve. And this is due to the fact that Starlink terminal does a frequent handover, switching from one satellite to another satellite. Now, if you ask me how frequent does the handover happen, I'll tell you this is something we're currently working on. We try to identify the Starlink handover strategy and frequency. Okay, so far we looked at the performance across different cities and in a single city and across different congestion control. Now let's try to answer the last research question, which is how about the weather? Here, this data is coming from the browser extension, and we focus on one city trying to understand how the weather affect the page transit time. And if we focus only on two weather conditions here, which is the clear sky day and the rainy day, what we can observe here is that the median page transit time is actually doubled in the rainy day compared to the clear sky day, which says that the weather had a significant effect on the performance of Starlink. So just to summarize, as of now, Starlink performance is comparable with other existing ISPs, but still it's not better than optical fiber links. A Starlink future inter-satellite links will boost that performance. Starlink connection quality significantly changed over location. Network latency can be doubled in a rainy day compared to a clear sky day. And that concludes my talk. And thank you for listening. I'm happy to take your questions now.